Well, welcome again to our journey into number theory, and we're in the middle of the proof of Dirichlet's theorem, and we've shown that the principal character can be extended to a meromorphic function with a simple pole at s equals 1, and therefore diverges as s goes to 1 from above. The most difficult part of the proof of Dirichlet's theorem is to show that if you've got a non-principal character, then L of 1 and chi is not 0, so its logarithm is finite. That is, its L of s and chi is bounded away from the 0 as s goes to 1. In the earlier examples, we did this by just getting some bounds, writing out the series and fiddling around getting some bounds and showing it was bounded away from 0, but to do this in general is more difficult. There are many different proofs of this of various levels of sophistication. I'm going to assume this result and finish off the proof of the theorem. So I'm going to assume that if chi is not principal, then L of 1 and chi is not 0. Finally, then, we can again state Dirichlet's theorem, and we can put all the bits together and finish off the proof, which again is still quite technical. So if a and b are relatively prime, a bigger than 0, there are infinitely many primes of the form ka plus b, k a positive integer. That means infinitely many primes in the corresponding arithmetic progression, provided the first two terms are relatively prime. Now, we firstly need to show that for each non-principal character, chi mod a, well, we've seen this result before, that I can take the logarithm of this using the Dirichlet series and then using the Euler product and using some Taylor series. And I need to show that this remainder here is bounded as s goes to 1. Now the problem is that even if s is real, which we will take it to be at this stage, and we're just going to go to 1 from above on the real axis, the problem is that we're still dealing with complex numbers, and so the logarithm is always a problem when you're doing complex analysis. So as I note here, even if we restrict s to be real, the values of that are complex, so it's necessary to worry about the fact that the log of z is multi-valued in the complex plane. One way around this, which is the way I'm going to go, is to try and define the logarithm of the L functions by using an infinite series to overcome the problem of the thing being multi-valued. And so to do that, I'm going to, well, essentially work backwards from what is the logarithm of L of s. And I take chi to be a Dirichlet character, s is real for the moment. I'm going to define this function capital G of s and chi by this infinite series, this double series here. Now it looks complicated, but all it is really, I've just worked backwards. I've taken the logarithm of this, so the log turns the product into a sum over the primes, and this thing here is just the series expansion of what's inside here, and that gives me this. So think of this g of s and chi as nothing more than the log of L of s and chi, but in the complex plane, and it's giving me a definitive value for this multi-valued logarithm. Now we just need to check a few little things. So if s is real, we want to check the size of this here. So the modulus of this is less or equal to 1 over p to the ks. S is real, and because each of these has modulus 1, and I can toss away the k and just get this. So we can get a bound on the size of this then. It's just the sum over the primes so from this it's just the sum over the primes less than 1 on p to the s minus 1, and that's just less than twice zeta of s. We've seen similar calculations in earlier sections. And now, since zeta of s converges for s bigger than 1, the same is true for g of s and chi. So g of s and chi is a continuous function for s bigger than 1. Now we just need to check that it does the right job, and so if z is complex for modulus of z less than 1, then e to the sum of zk over k is just 1 on 1 minus z. This again comes from the fact that we can get a series for this, and this series is analytic for mod z, real part of z less than 1. I simply now replace, looking back to where we want to be, I simply replace the z with chi of p to the minus s, which gives me this expression. And of course then looking back to the exponential of this g, remember we're thinking of this g of s and chi in here as a logarithm, so if I take the exponential of that, then the exponential turns the sum into a product of the exponentials of this sum in here. This sum in here we've just seen is equal to this. This gives me a product now over the primes, and this of course is our L of s and chi. In other words, this g does the right job. You can think of it as the logarithm of L of s and chi, so when you exponentiate it you get back to L of s and chi. So this g provides an unambiguous definition for log of L of s and chi. Moreover, if chi is not principal, then this is bounded as s goes to 1 from above, and that tells me that g of s and chi is bounded as s goes to 1 from above. This is for non-principal characters, and we're assuming that L of 1 and chi is not 0, and that tells us that g of s and chi is defined at s equals 1, because this is essentially just the logarithm of that. Now, the next thing we did in the examples in the warm-up to the proof was that we peel off, out of the sum, we peel off the first term, and then we get a tail. And we showed, just by doing various calculations and inequalities, we show that the tail is bounded as s goes to 1. So this is the first term. I'm going to call the tail r of s, p and chi. And I've got to look at the size of this. So we do our usual things that very similar to what we did in the earlier sections when we did the warm-up to Dirichlet's theorem. There's the sum, there is the tail. It's less or equal to, well, I can take the modulus of all of these numerators, they're all less or equal to 1. And I can replace the 3, the 4, the 5 and so on here with just 2. Using an inequality and factor it out, and as we saw before we get a geometric series which we can sum. So that gets me to there. Now I then go back and look at the r of s and chi. So that was a sum of this little r of s, p and chi, and again that we showed that this was less or equal to this expression. So we toss away the s as we did before, replace the p with an n, so instead of summing over the primes we just sum from n 2 to infinity, and of course that gives me a geometric, a telescoping series in here, which you can check when you telescope this one, you just get 1, so the totals are half. So that tells me, as very similar to what we did before, this tells me the r of s and chi is bounded as s goes to 1 from above. So that means we can write this g of s and chi, which again is just like the logarithm of the L function, as the sum over the primes of chi p on p to the s plus the remainder term, and the remainder term is bounded as s goes to 1 from above. Now the next thing we wanted to do was to pick out the primes that are congruent to B mod A. We did that before by looking at various sums and differences and multiplying by i's and subtracting and so on. I want to do this more, we need to do this more generally now, and we do it using our orthogonality properties for these characters. So that's going to come into play now. And so we call it the sum over the characters of chi of A, chi B bar. Well, that was 0 if A was not B, and it was 5A if A was equal to B. So we multiply the above formula for G by chi of B bar. Remember, B is fixed, and we sum over chi. So that then gives me this sum, and I can split this now because we we wrote this G as the sum of chi p on p to the s plus the remainder. I can write this sum as the sum over chi b chi of b conjugate times g minus chi b conjugate times the remainder. Now, reversing the order of summation on the left-hand side here and using the orthogonality properties that we had back in the earlier section, then we can pull out most of the terms are going to be 0 except when p is congruent to b mod a, p is prime, and the rest of the time the orthogonality relation is going to give me phi of a, which you can pull out the front, equals this difference here. Now finally, we've shown that this finite sum here, this is only a finite sum, and each of the r's are bounded as s goes to 1. So that sum is bounded as s goes to 1. I split this up into, this is sum over all the characters. So I split this up into the non-principal characters plus the principal character. Now, this first sum we've shown is bounded as s goes to 1. We've also seen, I should say, in Theorem 4.6 that the log of L of s and chi 1 is unbounded as s goes to 1. And so this g of s and chi 1 is just the logarithm of the L function. And so that is itself unbounded as s goes to 1. And that means we have here, this is finite. This goes to this one splits into a finite sum plus one that goes to infinity, and that forces this infinite sum here to diverge as s goes to 1, and that means there must be infinitely many primes p congruent to b mod a. Little section on Dirichlet density, we talked a bit about before. We worked out the Dirichlet density for the primes that are congruent to 1 mod 4. So I'll just recall we defined the Dirichlet density of a set of primes p by this limit. We take the sum of the s power, the reciprocal of the sth power of all the primes in the set. We divide by the log of 1 on s minus 1 and see if that makes sense as s goes to 1. So again, taking s real from the above, we take all the primes that are congruent to b mod a. And we've seen before that the L function of the principal character can be written as zeta of s times the product over the prime divisors of a of 1 minus 1 over p to the s. So when I take the logarithm of this, I can split this up into here. So the Dirichlet density then of my set of these primes that are congruent to b mod a is by definition just this sum. And now I simply plug in each of the expressions we had for this from above. So we have, we get L of the log of L of s and chi 1, which is this one. And then we get for the non-principal characters, we have this expression with the g and the remainders, and all divided by 1 on s minus 1. Now let's just see what's bounded. That one is bounded, so this divided by this is going to infinity, of course, as s goes to 1. So this over this is going to 0. This is bounded, that over that's going to 0. This term is a finite sum, and so this is a finite number dividing by this is going to 0 as well as s goes to 1. So I'm just left with the log of zeta of s over the log of 1 minus s. And of course we know that that one we saw before, that goes to 1. And from what we had above, we had a 1 over phi of a from the earlier formula for before we substituted this in. We had a phi of a multiplying this expression, so it's 1 over phi of a here. So all that collapses, that limit collapses down to 1, and we just get 1 over phi of a, which is kind of what we might expect, in fact. So we get 1 over phi of a, since there are 3 terms in the, since the 3 terms in the numerator, the last 3 terms are bounded above, above are bounded as s goes to 1 from above. So that's a very nice expression for the Dirichlet density. You would sort of expect there would be 1 over phi of a. It makes sense. That's what you'd expect, and that's what, in fact, what you get. Now, for the the remaining piece was that L of 1 and chi was not 0, and Dirichlet himself used some rather deep results from the theory of quadratic forms to prove this result. So I'll just say a quick word about what he did here. The results were connected with the class numbers for quadratic extensions of Q. If you've done some algebraic number theory, you may have come across the class numbers. Essentially, certainly back in Dirichlet's time, it was all done in terms of quadratic forms. So given a quadratic form, ax squared plus bxy plus cy squared, a, b, c integers, we define the discriminant of this as b squared minus 4ac. For fixed d, once you fix the discriminant, you then take all possible quadratic forms with that discriminant, and you look at the set of integers that are generated by these forms as x, y take all integer values. This partitions the forms into equivalence classes, and the number of such equivalence classes is called the class number corresponding to this discriminant d. Now, of course, it's not at all obvious a priori that the class number is finite, but this in fact was shown to be true by Gauss. Just as an example, if we take x squared plus y squared, take all things of this form, and x squared plus 2xy plus 2y squared, all things of this form, these both have discriminant minus 4, so that's the d here, and it turns out they both represent the same integers. So if you let x and y vary through the integers and you take all numbers of this shape, all numbers of this shape, they turn out to be the same. And in fact, it turns out then that the class number for minus 4 actually turns out to be 1. On the other hand, if I take numbers of the form x squared plus 5y squared and numbers of the form 2x squared plus 2xy plus 3y squared, both of these have discriminant minus 20. But they're not equivalent, because the latter represents the numbers 3 and 7, but you can't represent 3 and 7 by a quadratic form of this shape. So that tells me the class number for minus 20 must be at least 2. Well, in fact, it's exactly 2, but it had to be at least 2. Divishley showed that if p is bigger than 3 as a prime, then the class number turned out to be a multiple of L of 1 and chi for non-principal characters. And since the class number is at least 1, he gave a proof that L of 1 and chi could not be 0. Now, that's not the approach taken nowadays. There are various different proofs of this. All of them are quite difficult and all of them quite technical. And I'm not going to go through any of those proofs. I might refer you to Jamison's rather lovely book called The Prime Number Theorem by Jamison. He has a very nice proof in there that is reasonably, which is quite accessible. It's just long and technical. There are many other proofs floating around of various degrees of technicality and assuming various different other results along the way. But I decided to skip over the proof of that particular result. I've got one more video for this chapter, and I'm going to have a look there at actually evaluating L of 1 and chi for various examples and show you some interesting facts about L of 1 and chi.